Hi everybody, my name is Paul. I'm going to present to you the research that I did this year during the RISC program. My project is called Risk-Aware Safety Assured Model Predictive Path Integral Control on F1Tenth Racing Cars. The motivation behind our work is that autonomous vehicles are safety critical systems, as you can see in the video on the right-hand side. The one vehicle is cutting off the other vehicle. We can conclude that small errors can quickly result in dangerous scenarios. So we want to achieve risk-aware behavior and provide safety guarantees for path planning or autonomous driving in general, while maintaining high flexibility and adaptability. Previous work includes model predictive path integral control, a framework proposed by Williams et al. At Georgia Tech Group in 2016. The way MPPI works is that it, as you can see in the video, predicts future states of the car. It does so by using a kinematic bicycle model. So xk plus 1, the next system state, is computed by using a discrete time control system. And the control input uk consists of the steering angle delta and the throttle t. The system state q consists of xy, which are the position of the vehicle, theta, which is the yaw angle, and v, which is the velocity. Notice that it takes 2 time steps for the control input u to have impact on the system state. This will become important later on. Model predictive path integral control works in a way that it samples a lot of trajectories around the nominal control. So as you can see, for the red vehicle, there are a lot of trajectories that the red vehicle could take. Some of these trajectories might be unsafe to take. So what we do is for each trajectory, we compute a cost function. And this cost function could have a high cost if it's unsafe to take. For example, if it goes off track. So in the end, when we synthesize an optimal control, what we do is we look at the cost function for each of these trajectories and then synthesize the control input by looking at the average of weighted trajectories. In this way, we compute the optimal trajectory, which is orange in this example. So how to make them safe? We can use control barrier functions. And the intuition behind control barrier functions is that we have a safe set. As you can see on the right-hand side in the figure, it's the blue cone. And the formulation behind CBF is that we want to ensure that for each system state inside this safe set, there exists control input u, such that the system state of the next time step also stays inside the safe set. This can also be derived for high-order discrete time cases. And now it is important to think back to the kinematic bicycle model, in which we said it takes 2 time steps for the control input to have impact on the system state. So we might want to do we might want to choose a relative degree of 2. You can pause the video, feel free to pause the video to look at the mathematical derivation of the high-order discrete time case. And our proposed solution is the risk-aware, safety-assured model predictive path integral control framework. So essentially, we use model predictive path integral control baseline as proposed by Williams et al., which provides flexibility and adaptability as we requested in the beginning. The problem about MPPI is that it lacks risk awareness and is vulnerable to uncertainties, especially in cases of highway overtaking, in which are multiple agents and vehicles that we need to keep in mind. And therefore, we include a safety filter and a risk awareness term in the cost computation, which both are inspired by control barrier functions and are used in a high order and discrete time case. So we refine the model predictive path integral control framework. We first of all sample around the nominal control and use CBF-inspired risk awareness penalization in the MPPI optimal control input synthesis. Then we pass this optimal control to the higher order discrete time control barrier function filter to decide if the trajectory that we predicted is safe to take. If so, the CBF function is feasible, then we execute the first time step of this optimal trajectory. Otherwise, we would employ a contingency strategy and just try to brake to do an emergency brake. So how does this perform? We compared it to state-of-the-art methods like shield MPPI. And as you can see here in the top figure for shield MPPI, It does not perceive the vehicle that you can see right now in the left lane. So it had to switch back to the right lane between the two cars in a very narrow space. So as you can see, it crosses the safety distance from the car going in front of the ego vehicle. Yeah, this could be dangerous because it risks that it collides with the other vehicle. And for our proposed framework, as you can see in the bottom figure and simulation, it waits until the opponent vehicle in the left lane that's coming very late passes. So it is more risk aware than the shield MPPI version. As you can see right now, it waits until the opponent vehicle comes and only then starts overtaking, being very safe and having safety guarantees. So we wanted to try that for F1Tenth vehicles. First of all, we implemented it in the F1Tenth simulator. So as you can see, our ego vehicle approaches the other vehicle, the opponent vehicle, notices it, and plans a trajectory that goes around it with a safety distance, merging to the left lane. As this was successful, we wanted to test it on real hardware. So we came to real-time multiple path integral control evaluation on F1Tenth cars. As you can see in the video, our framework runs in real time without any external processing unit or power consumption or computational cost. So what are the results of our work? We provided safety guarantees and raised risk awareness in the framework, and we verified that on not only F1Tenth hardware, but also in simulation with several multi-agent systems, doing the computation on board without having to connect to external processing units like other state-of-the-art frameworks and proposed works. What could be future work? First of all, we could integrate covariance steering into the sampling process in order to more leverage our risk awareness term in the cost evaluation. Furthermore, we could improve the contingency strategy and not only do an emergency brake, because that's not always the most optimal thing to do. Last but not least, we could also use more complex system dynamics modeling or use more interesting test scenarios. And at the end, I want to extend a big thank you to Iwe, my mentor during the summer, John, the head of our lab, the Drive Lab, and Rachel, the RISC program organizer. You've all been very helpful throughout the summer, and this would not have been possible without you. So I really appreciate the work that you did, and I hope that a lot of students in the future can have the same opportunity as I had. Thank you.